To discuss geotechnical engineering, you have to start by talking about soils. What are soils? Now, the definition of a soil for a civil engineer is an uncemented or a weakly cemented accumulation of mineral particles formed by weathering of rocks. Now, what do we mean by uncemented? Now, when we say uncemented, we mean that the particles of your soil are not bound to one another by any bonds or anything like that. So they are individual particles that are in direct contact with each other, but no bond exists between them. That's why if you have soil in your hand, then you just open your fingers, they will just slide through your hand and fall to the ground because there are no bonds between them, but they are in contact with each other, which is important because the friction between the particles and the strength from that friction will become very important in geotech, especially if you're going to build on top of soil. And the problem with uncemented is that it makes soil to be susceptible to erosion. Now, because they are not unbound, they are not bound to each other, then when something like water or wind comes and exerts a force on them, it will likely succeed because the particles are not attached to anything that will hold it down. Unless you exert a force that causes the particles to slide against each other, then the friction will create some strength between the particles and it will fight off. But because they are uncemented, they are more susceptible to erosion. Now, we say an uncemented or weakly cemented accumulation of mineral particles formed by weathering of rocks. Now, when we say weathering, we mean that soil come from a bigger particles that has broken down and broken down over a period of time. Now, even if you have a mineral rock that keeps breaking down like a quartz, maybe it will end up being small, finer particles of soil. Where it actually weathers is very important because soil, you can have two types of soil. Now, the first one is called residual soil. Now, residual soil is when the products of the weathering process remain at the original location. So a rock or a mineral can break down and then the product of that breaking down process are still at that original location. So products of weathering remain at original location, and we call those types of soils residual soils. An example of that is that if you find a rock inside of a glacier, so what will happen is that over time that rock will keep breaking down, but because it is inside this block of ice, it will remain and not be able to move anywhere. Imagine a rock on a mountain and then there's like rain, there's a river, there's wind, and then it comes and weathers down the rock, and then the product of that weathering process gets transported by water or your river or whatever, and those are called transported soils. Two types of soils: residual and transported soils. Now, transported soils are when the product of the weathering process are transported and deposited at a different location. Now, weathering is the breakdown of rock. Now, from a parent rock, and then it breaks down into smaller and smaller fragments. One is the physical weathering and the other is the chemical weathering. What do I mean by physical weathering? Now, physical weathering, it's a process whereby there is a physical breakdown of your rock. So it breaks down physical in a way that we can see and observe, and it does that without changing its chemical composition. Now, what does this mean? It means that if you have a rock that has a certain chemical composition, maybe a certain mineral in it, when it breaks down physically, I mean like one rock, you hit it and then it breaks into two, it breaks into five, it breaks into pieces, but it still contains the same minerals, the same chemical composition as the parent rock. So it still have the same chemical composition, as the parent rock. And when a soil still contains the same chemical composition as the rock, we say that our soil is bulky. And this is where you'll often see in geotech saying we are using the bulk density, or we should calculate the bulk density. Now, types of physical weathering where your rock can break down physically. You can have frost. Now, when you have frost, it means that water creeps into the spaces between the rocks. So it will creep in like this. And then your rocks will become hydrated. But then, after it comes in and makes your soil wet, when the weather conditions change and it becomes very cold. Now, an important component of weathering is that the causes are mainly from environmental conditions, hence the word weathering. Now, as the water creeps inside the particles of the rock and then it becomes cold, the water in the voids will become ice, will become frost. And as they get colder, one characteristic of water is that when it becomes frost and it starts to freeze and become ice, it expands. So it becomes larger inside. So when you take a bottle of water and you put it in the freezer, when you take it out, it seems as if there's no longer any space in the bottle. There's even water in the hole that you are going to drink in. There will be ice in there. So your water becomes bigger in size. Now, if it creeps inside the particles of soil and then it expands, it will begin to exert some pressure on these particles and then break down this soil. The second one, you can have abrasion. Now, with abrasion, it is the usual breaking down that we are used to, whereby you can have erosion. An example of abrasion is erosion, whereby the wind will come and then it will exert a force on your rock, and then it keeps breaking down little by little from the friction between the air and the rock particle. Another physical example of physical weathering is the weathering that comes from biological causes. An example of biological is the roots of a plant. Now, if you have soil on top of and you planted a tree on that soil, the roots will start to grow, and the more they grow, they will try to force their way through the soil, and then they will start, as they try to make way for themselves, they will push the soil out of the way, breaking down the particles. Remember that the particles of soil are not bound to each other, so it is possible to force something through it, and when you do that, your rock breaks down and then becomes smaller particle. That's why it is not smart to build a house next to a big tree, because the roots can be so big that they make your soil below become very weak and then your house become susceptible to settlement or anything like that. And that is physical weathering. It is when the rock breaks down physically into smaller fragments without changing its chemical composition. Now, a different type of weathering, it's called chemical weathering. Now, chemical weathering involves alteration of rock and mineral composition through chemical reactions with substances in the environment. So here it is not physical. There will be an alteration in composition as a result of some chemical reactions that will take place between the rock and substances in the environment. Now, what do I mean by that? I mean that your mineral your mineral rock could be one thing now, and then there's some sort of reaction that takes place, and then it changes what it is. Now, an example of a chemical weathering, one of them is hydrolysis. Now, hydrolysis. Now, hydrolysis is interesting, is when water reacts with the minerals inside your rock. So hydrolysis includes water reacting with the minerals in your rock. An example of this is when you take a simple soil and then you add water to it, and then it changes composition and becomes a clay mineral. Now, when you take soil and then you add water, it will become what we call a clay mineral, and this is a result of the chemical reaction that takes place with your rock. Now, another example of a chemical weathering will be oxidation. Now, with oxidation, it's when oxygen comes and then it combines with some element in the rock and then forms a new material, changing the chemical composition of your rock. An example of this is if you have oxygen, some rocks will have some iron in it. Now, when this oxygen comes and combines with iron, it will form what is called rust. Now, you will observe that from some rocks or some pieces of soil, you will observe some rust there, and that is a result of oxygen combining with iron, and then there's some oxidation that results in rust. Another example of chemical weathering is called dissolution. Now, dissolution, as it means, it's when you have maybe water comes and reacts with your soil, and the minerals in your soil will start to get dissolved. We start to get dissolved because some minerals have that ability to get dissolved. They are sort of salt, and when they mix with water they dissolve, and then you will not see the difference between them and the water that they are reacting. Now, in dissolution, when your particles react with dissolve, they will form some crystalline particles that are smaller than 0.02 millimeters. They are so small and they are so wet because they are dissolved, they are mixing with water, and that is exactly the composition of what we call clay. Now, your clay is a result of your soil or rock being mixed with water, and then the minerals in it that have the ability to be dissolved will be dissolved to form a crystalline particle. The interesting thing about clay is that the soil doesn't actually react with the water, it just mixes with it. and then this water will come and attach itself to the walls of the soil particles. So this water is just attaching itself to the walls of the particles of the soil. So it doesn't actually react with the soil. That's why when it rains and water mixes with soil, it will be very clayey. But when the sun rises again, this water is only attached here and does not mix or react with the particle. Therefore, it can evaporate again, and then your soil becomes dry. Now, when water attaches itself to something like this, we call it adsorption. It is not the now. Some interesting thing about soil. Number one is that particles of soil can range in sizes. The range could go up to 100 millimeters, while some could be less than 0.01 millimeter. Now, in this range, the smaller they go, we start to call them fine soil, and the bigger they become, we start to call them a coarse soil. An example will be gravel and things like that. Example of fine soil could be sand or cement. Cement is very fine, so it has very small particles that could be less than 0.01 millimeters. Now, soils are also highly variable. Now, when we say that they are highly variable, we mean that properties vary from point to point. So whatever you find at this point may not be the same as what you find 100 meters away. So if you calculate the strength of your soil here, doesn't mean that it is the same strength 100 meters away. So there are very large variations in your soil over small distances. So one nature of soil is that it is highly variable. Now also it does not have a linear stress strain relation. Now when you have a material like steel, for example, when you draw the stress strain response of a steel material, it begins as very linear, where the relationship between the stress and the strain produce a linear relationship before it goes and becomes plastic. Now, with soil, it does not react that way. So your stress and strain response, it is very variable. Now, soils are also inelastic. Now, by inelastic, when I say inelastic, I'm saying that they are not elastic. I'm not saying that they are plastic. I'm saying that they are just not elastic. We say that they remember what happened to the past. So when you have soil and someone comes with a shoe and they step on it, the soil will change shape and you will see that someone walked here. You will see the shape of the foot. So it changes shape. When it experiences strain, it doesn't bounce back into its original shape, like when you have a rubber or something like that. So it is not elastic, but it is not plastic, because someone else can come and step on it and then it changes shape into another shape that could even help it go back to its original shape. So it is very inelastic. Now another nature is that it is anisotropic. Now when you say a material is anisotropic, you say that it has different properties in different directions. So when you exert a force on the side, it may react one way, but when you exert a force on the other side, it may react one way. It is just like when you use when you use what's this? When you use a plank from a tree, it is strong in one direction but very weak in another direction. So it will be like this. And if you exert a force in this direction, it will be weak. But if you exert a force, then all of this make it very strong. So anisotropic means that soils have different properties in different directions. Now, the last one is that it has a multi-phase system. By multi-phase system, we mean that if you zoom in into the soil, you will realize that it has solid particles. It has solid particles, and also it can be surrounded by water particles all around, water particles, while also the spaces in between here where there's no water and no soil particles, you may have air. So these voids here will be filled up by air, or the voids on this side will be filled up by water, while the soil itself is a solid particle. So it has a multi-phase system that exists of solid particles, water particles, and air molecules. So that is the nature of soil. In the following videos, we'll discuss its strength, the uses that we have to it, how to classify it, and how to make it strong so that we can build buildings on top of it.